Okay, let's share it again. Okay, now so characteristics is so to represent such input output characteristics when input is varied with time, what do we need with algebraic equation? With an algebraic equation, and we need a differential equation. So we use a linear differential equation. And most there are systems where we need to go for a nonlinear differential equation or variable differential equation or such. So now, what will be the order of the differential equation? That extremely depends on the system. It might be of order 0, it might be of order 1, it might be order 10 or even more. It depends on how you build the measurement system, how it is behaving with the input. So, usually, so that's what I say is that it may be linear differential equation, it may be non-linear. The differential equation may be time varying, it may be time invariant. Usually or generally, we use linear time invariant system for such. So to model an instrument where the input is varying. So now from this point, it is clear that when you are trying to use a measurement system or a measuring device for some to design and system or to design and control loop or to measure some input. So you need to know different parameters associated with the static characteristics. You need to know the system measurement system model by with the help of linear differential equation, or in other words, if you do the Laplace transform, you need the transfer function. You need to know the transfer function of measuring instrument in S domain. So these are the all things you need to know before you start operating or before you start applying any measurement system to any measuring device, to any system or any control loop or any particular application. Okay. So is that clear? Tell me up to this point. One thing is it clear? And you people are hearing everything clearly to me? That is also very important. Or if you have any query, so this is an introduction why we need dynamic characteristics, or in other words, why we need to model a measuring system with the help of differential equation or either in the Laplace transform, or we need to model the measuring system, or we need to know the transfer function of the measuring system more precisely. Okay, fine. So very good. So let's proceed. So now, if you want to measure, if you want to model a measuring system or instrument, which we call the dynamic characteristics, how you can model it. That's what we said that we assume. So initially we said that we need to model it with the help of differential equation. And then there may be linear, it may be non-linear, it may be time varying, it may be time invariant. So we assume for simplicity, because it is our first course, we assume that the system is LTI, that means linear time invariant system. That means the dynamic characteristics or the dynamic equation is not changing with time, and it is linear, coefficient are constant, all those things. So for an LTI system, the input output can be written with the help of a uh, with the help of a differential equation. Now let's see how we can write it with the help of a differential equation. Now let's look at the equation 2.1. Okay, so it is arbitrarily named. So let's look at the equation 2.1. What this equation says, this equation says this is a differential equation. And what is Q0? Q0 is is the measured Q0 is the output and Qi is the input. Okay, so Q0 is a function of time. They did not write it, so we should write it Q0 as a function of t, and then we do the difference. There is nth order difference. If you know this differential equation, and if you can solve to know an input output relationship, because you need to know the initial condition of that, otherwise you cannot solve it. Now here it is needless to mention that an minus 1, all such a's are the constant. They are not time varying function. That's what we assume. We said it. And all the b's are the constant. They are not time varying parameters. So by this way we can write a input output. We can model an input output of a dynamic system. So it is a kind of in generalized form. So in general we can write such model. So now we can do Laplace transform, because now you are familiar with Laplace transform. You are reading the control class, so you are familiar with the Laplace transform. So with such Laplace transform, what you can do, the equation 2.1, you can transform it, and then you will get the equation. It is written here. So it is, you see that it will be an sn, s is the Laplace domain, plus an minus 1 sn minus 1 plus dot dot dot, and then a1 s plus a0, and then output q0, that will be the frequency domain q0, capital Q, it is written, of s, and then right hand side will go bm s to the power m, and so on. So, and then our input will be qi in s domain, s, not in the t domain. Now you see, if we do the output by input, that will become the transfer function. We are writing hs. Why we are writing hs, not gs? Gs we generally write to plant. Hs we generally write as a feedback, and measurement system is used in the feedback. That's what hs is, very customary. We can write the hs. So it will be bm s to the power m like this to b0, and an is to the power n like this. So it is a general expression in Laplace domain of the transfer function of an instrument which is required when we measure some input varying, time varying input quantity. So this is in general the transfer function of a measurement system. Now let's come. So I think up to this point there is no query. Okay, there is. Oh, again voice is breaking constantly, 958. Oh man. Let me do one thing. Let me try with my hotspot or something. Okay. So if voice is breaking constantly, what can be done? So we need to try something else. Today is not a good day for us. Or I can change my position or something else. So I'm trying to change my position. So let me say that if it is good. So now can you hear me properly? I change my position. So or the voice is breaking constantly. Please respond.
Yes, sir, you are audible.
Okay, now maybe it is better. I came very near to my Wi-Fi. So let's try it now. So, so let me explain then this slide again. It's very irritating. It's continuous interruption. So 2.1, most probably you have understood that this is an input output relationship where all A's are the constant, not time varying, and nth order differentiation is, and the right hand side there is a mth order differentiation. And then if we take the Laplace transform of such expression of 2.1, we'll get something an s to the power n plus n minus 1. That's so we'll get this equation. And then if we do the output by input, which is hs, I was telling why it is hs, because it will be used, it is a major transfer function of a measuring device. It will be used in a feedback loop, and you know that GS is used in the control system to represent the transfer function of a plant. HS is used to represent the transfer function of a feedback system. And then that HS is actually the measuring device. That is what we are writing HS here. So HS will be BM SM plus BM minus 1 SM minus 1 like this, and denominator. So this is a, in general, nth order differential equation or nth order system what we can write in the form of transfer function. So to measure any input from the output, we need to know this transfer function, and we need to solve the transfer function with some proper initial condition so that we can know the input from the output of such measurement system. Now you tell me that whether you understood this page properly or not. Okay, maybe you understood this. Okay, fine. So now if any query, any point of time, you can ask, you can write. So now let's proceed. So this is in general a nth order n, okay, n for nodes, that nth order transfer function of any measuring device. Now suppose what we generally do, or let's say the right hand side of this equation 1, it is not necessarily that all the BMs will be 0 instead of B0. So we can assume such, but it is not necessarily, and definitely it never goes such a way, because you know, if HS is this transfer function 2.2, and if you solve the characteristics equation numerator, that means Bm h to the power m plus Bm minus 1 h to the power m minus 1 plus dot 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 equals to 0, and solve this as a algebraic equation, you will get m number of roots, and those roots are known as the zeros of the system. And then if you solve the denominator, which is an s to the power n plus an minus 1 s to the power n minus 1 plus dot 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 plus a1 s plus a0 equals to 0, and if you solve the denominator equals to 0 to this algebraic equation, you will get the n number of roots, and this n number of roots are called the pole of a system. So we have the m number of zeros, and we have the n number of poles of a system. Now, it is not necessarily that any measurement system will be having no zeros. So equation 2.3 says that this measurement system has no zeros. So but for simplicity, let's proceed. There might be 0, no issue. We'll take care of that. And here we are assuming that there is no 0, only poles are present. So, but there may be 0 definitely, and then there will be B1, B2, all those terms will be there. So now if we assume a nth order differential equation or transfer function which has no 0, so all the B's apart from B0 can be eliminated. So our HS will become B0 by an s to the power n plus an minus 1 s to the power n minus 1 dot 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 plus a0. That will be the transfer function. Now for the time being, it is extremely not necessary to assume that there is only B0. There might be B1, B2 and all those things. But one thing is necessary, that number of zeros will be less than number of poles. So M will be less than N. Okay. So now the poles are of extreme importance. So based on the number of poles, that means based on the values of N, N for nodes, we can classify our measurement system as the order of the measurement system: 0 order, first order, second order, third order, like that. Okay. So based on the value of n. So if n value is 0, then it will be 0 order instrument. If n value is 1, it will be first order instrument. If n value is 2, it will be second order instrument. So this is the things we can tell. Now tell me if you hear all the things properly and it is fine to all of you. Okay, now let's come to the slides. So here what we say that, so we have zero order instrument, we have first order instrument, we have second order instrument. Then how it will look like? Now let's assume. So for the time being, if it is a zero order instrument, so n will be 0. So we have a0 s to the power 0, which is a0. So what will be our hs? So the first order, sorry, zeroth order instrument. So for zeroth order instrument, n will be 0. So in such case, it will be b0 by a0. So when we assume all the coefficients a1, a2, all those things, other than a0 and b0 are 0, then equation 2.3 will comes as the a0 q0 will be equals to b0 qi. Now if you do the output by input, which is q0 by qi, will be b0 by a0. And if you write the output q0 will be equals to b0 by a0 into qi. That means what is b0 by a0? b0 by a0 is a constant, qi is the input varying parameter. So this is ideal instrument where the output is varying instantaneously with the input. There is no dynamics associated with that. And b0 by a0 is the constant. So this is called the zeroth order instrument. So q0 will be equals to b0 by a0 qi, or q0 will be equals to kqi. So if you want to know the output, input, from output, you divide it by a constant k, you will know the output. Sorry, input. So output will be a constant multiplication of input, and the way when the input will be varying, output will vary similarly instantaneously. There is no dynamics, and the gain k is known as the static sensitivity. So zeroth order instrument is the ideal instrument which everybody should prefer if there is anything available. So from the equation 2.4, we will see that no matter how Qi vary, how fast or so, the output will perfectly follow the input, and there will be no distortion, no time lag, no dynamics associated with that. So zero order instrument is the ideal instrument or perfect dynamic instrument which every instrument engineers prefer, because the output can follow the input perfectly without any time delay, without any lag, without any distortion. And just you multiply some constant with the input, you will get the output. That's it. And you know, and whatever output you are getting, you divide it by that constant. You know the what will be the input. So, and that constant is known as the static sensitivity. So this is the zero order instrument, and everybody prefers zero order instrument. This is an ideal and perfect dynamic instrument. And if any instrument you get for zeroth order, you should choose that for your application. Okay. Tell me any query up to this one. Okay, no query. So now let's come. What could be the if zero order instrument exists, and can you give some example of zero order instrument? So definitely you can give some example. For example, if you assume, if you see the circuit, so there is you see the circuit. So potentiometer, it's a very favorite circuit. Potentiometer, where input is the EB and there is a length. So through the potentiometer you can measure the displacement. We will read in detail while we'll come while we'll be reading in displacement measurement. But now here we see with the help of potentiometer how you can measure the displacement. Suppose we have a battery EB and which is attached with the resistance of length L, and then the resistance has a slider. The slider can move over the resistance and it has some distance from the zero, and then E0 will be the output. So E0 you can measure with the help of a voltmeter or something digital meter. Now how E0 is related with the EB? So E0 will be EB divided by L into Xi. And now if you do that, Xi is the input, EB is constant. So EB by L is constant, length is not going to change. EB is the input voltage, it is not going to change. We are not assuming that the voltage is decaying with time, voltage is constant, and then EB by L is a constant, we can write it as a K. So E0 will be equals to K into Qi. So given a linear distribution, so that you see that E0, which is the output, is a proportional to Qi, which is nothing but Xi. So the output is proportional to the length of the slider it moves. So By measuring the output, you can measure the length of the slider move, and from there you can measure the displacement. So that way you can measure displacement with the help of potentiometer, and such a measuring device, the measurement of displacement with the help of potentiometer, is a good example. Is a good example of an instrument of order 0. And you see that the gain is K, which is EB by L, and we know that the high gain is very important. So if you increase the voltage EB, the gain will be high, or the sensitivity will be high. And the measurement error, what will be the measurement error? Measurement error will be the EM, means KQI minus E0, which is 0 for the ideal condition. We are not assuming the random disturbance and all those things. So in such experiment or such measurement, if we plot the right hand side figure Xi versus E, how it will look like? It will look a perfect straight line. So the instrument is linear and zeroth order system. Whatever input comes, the output will give accordingly. There is no delay, no lag, no distortion, or not any dynamics associated in between the input and output. So such type of instrument is very ideal, and it is very rare to get it such instrument for any particular application. However, this potentiometer is a good example of such instrument. Now tell me any doubt up to this point. Okay, so everybody understood it properly. Now let's proceed to next. Now first order instrument. So in first order instrument, definitely we have all the coefficient. Only two coefficient will be, because n will be 1. So we will get only dq by dt, q0 by dt, and there will be constant a0 q0 and b0 qi. So if you do q0, or if you do the Laplace transform, what you will get? You will get v0 by a0 divided by 1 plus a1 by a0 into s into qi. So Q0 will be some constant, which is B0 by A0, divided by 1 plus A1 by A0, which is tau, into S into Qi. Now you see Q0 and Qi are not related by multiplying a constant number. There is one S in denominator. That means there is a differential equation of order 1, and you have to solve in order to get Q0, or in order to get Qi from Q0. So there are two constant here. You see, one constant is K, which is V0 by A0, which is called the static sensitivity, and there is another constant tau, which is A1 by A0, which is called the time constant. So if you want to use a zeroth order instrument, there is only one constant associated with it, that is K, which is called the sensitivity or static sensitivity. If you are having a first order instrument, there are two constants. One is K, which is called the static sensitivity, and another is tau, which is called the time constant. The static sensitivity is about the gain. That means how much, when suppose input is not varying, it is constant, then it will be K into Qi. That means how much amplification in output you are getting from the input. And then tau is the time constant. That means it says that how quickly the suppose you give some step input, and how quickly the system output is reaching to steady state, that represents the tau. So so this is the first order instrument. So if you have a first order instrument, your transfer function will be something by input by 1 plus tau s, and always you write in the form of 1 plus tau s, not something tau s plus 1. So in such case, tau will not be time constant. So this 2.8 equation 2.8, you be very careful. So if you want to write the equation 2.8, you have to write in such a way that 1 plus something into s, and on the top there will be gain. In such cases, the gain will be static sensitivity, and the tau will be the time constant. If you write this equation as some gain divided by s plus some constant into qi, then that will not be the time constant. The student usually do this mistake. So now, is there any tangible examples which you can give as a first order instrument? Let's see if there are any query. this point. Okay, there is no question. So now the question is, can you give any example of a first order instrument in day-to-day life? The very quick and easy and example is the temperature measurement. So suppose you give, let's see that you want to measure temperature. So you touch the mercury bulb in the measure end, and then what happens? The mercury bulb slowly tries increasing. If the temperature is constant, so you touch the temperature, that means there was no temperature on the mercury bulb. Suddenly the temperature in the mercury bulb rises. So what happened then? The mercury start rising slowly, and you wait for 2-3 minutes. The mercury keep on rising. At some point it will reach steady state and it will not rise anymore. So if you plot it, that mercury column with the time, you will see that the column is 0, at time is 0, and at that time is 0, you touch this heated surface, and then this mercury column length is keep on increasing, and it reaches in the steady state, and then after some time it does not increase. And then if you convert this mercury column, or if you scale the mercury column as in degree, centigrade or degree Fahrenheit, whatever is the unit of temperature, then what will happen? You will see that the temperature is gradually rising, and after some time it reaches steady state, it does not rise. So this is a perfect example of first order system. But if it is a zeroth order system, there will be no dynamics. What I mean, there will be no slowly rising. If it is a zero order system, you give some temperature, immediately it will show this much temperature. There is no rise time. So as it is, it has dynamics, it's rising, it takes time to rise, so it becomes a first order system. So, so this is a very good example of first order system, temperature, and now you understand why the temperature thermometer is a first order system, because it slowly rises and for fixed temperature it settles somewhere. Now the point is, which one is good? Suppose I want to choose between two temperature thermometers, want to choose based on the dynamic characteristic. So one thing is that the gain K, the temperature which is thermometer which has the more gain, it is good, that is fine. But from the dynamic point of view, dynamic characteristics point of view, the thermometer which rises very quickly, that is much better than the thermometer which is rising slowly. Suppose we have a thermometer which is rising very quickly. So and you need to wait for say half a minute to see the steady state. Now suppose you have another thermometer which rises very slowly and you need to wait for 5 minutes to see what the steady state is. And then which one you will prefer? You will definitely prefer the thermometer which is rising very fastly and reaching steady state quickly. So the rise time is very important. That means the if rise time is small, you need to see. If rise time is small, you will prefer that way. Now the dynamic behavior generally can be studied. So when I said that we need to study the dynamic behavior, what will be the output, what time very input. So initially what we do, we generally give some known type of input, not the known input, known type of input. What does it mean? I mean we generally try to give some impulse input. Impulse input is suddenly something, and then we give some step input, ramp input. That means that input is changing slowly with time, with constant with time, and then sinusoidal input. That means it is varying. So we generally prefer, these are called the test input. So we generally prefer those test input signals: impulse, step, ramp, and sinusoid. And we want to see how the output is performing based on such inputs. And in the book you will see all the type of instruments, first order, second order, third order, and all. People used to give such input, known input, and then they used to see that how the output is varying and try to characterize the output. That is what the textbook holds. You also read that. So now if you see the first order instrument, so uh, so if you try to solve this equation, Q0 equals to Qi 1 plus tau is, either you solve using Laplace transform, you do inverse Laplace, you get the time domain expression, or you solve it by solving differential equation. Whatever the way you solve, you will get Q0 will be equals to e to the power something into Qi. So and then if you want to plot it e to the power something into Qi, you will see that initially that is 0, and gradually it is increasing. So this curve is very important. If you see that the curve, which is the step kind of thing, this is the curve, then you will see this is major quantity. At some point of time t there was no nothing, and then suddenly there is something which is called the step input, and then you see the output how it is slowly increasing and gradually increasing. At some time it reaches the steady state and never increases. So this is the instrument output and this is the measure quantity. So if measure input is having a step change, that means it goes some magnitude from 0 or some low value at the time t, and then you see that how the output we receive. Then in the thermometer you see that from 0 gradually increases and then it's saturated. Now, what will be the time constant tau? The time constant tau is defined as the output quantity Q0 to reach 63% of its final value. So, this is very important question generally people ask in Viva and all. What is the time constant of a first order system? So, time constant generally is associated with the first order system. Okay, so no second order system you will not get time constant. You will get some other parameters. Will come very soon. So in first order system, time constant is the time which takes 63% to reach the 63% of its final value. So that time, so here you see the output reaches the 63% and the time is tau. So at the time tau, it will reach the 63% and the tau is known as the time constant. So if you have a first order instrument, you need to consider its dynamics and then you need to choose accordingly whichever you want to choose, and whatever you choose, you need to know the k and the tau values, and then you feed that HS to your control loop to get the overall transfer function. So now if we want to see that what are the performance parameters of the first order system. So generally the dynamic characteristics are characterized by the two things. One is the rise time and another is the settle time. So what is the rise time? So you remember this tau is the time constant. Now what is the rise time? So this output is gradually rising. So when we say that, what will be the rise time? So rise time is the response when the output reaches 90% to its final value, final steady state value. So when it reaches, at the time it reaches the 90%, that time is called the rise time. And then what is settling time? Settling time is it's the time to reach and stay within a steady state tolerance value plus minus. Sometimes it is considered 5% tolerance, so plus minus 5% of the final value. If the final value is 1, so 5% is 1.5 and sorry 1.05 and 1 plus and 0.095 or something. So when it reaches in between that band and it never leaves that band, so if it reaches and then it leaves, so it will not be settling time. It reaches the band and then with this tolerance value and never goes outside the band. So that point it reaches in such band is called the settling time. So if you know a system of first order whose rise time is much high, so that means if the rise time is high, that means it is taking longer time to rise or to reach the 90% of the step input value. So it is not preferable. If the rise time is less, that means it is reaching quickly to 90% of the step input or final value, then it is preferable. So for first response, we require a small value of tau. So to get the first response, we require a small value of tau, and for small value of tau, we'll get response very fast and rise time will be very small, and need to know which parameter to reduce so that. So suppose you are designing some measurement system or some measuring instrument. So then there, what is our objective? Our objective is suppose the system is the first order. We will come for the second order later. Suppose the system is the first order. Then what is our objective? Our objective is to reduce the value of tau. Now you will change the measurement system parameters. Parameters means the hardware parameters. Sometimes it's a spring constant, sometimes it's something else. So this mercury bulb size, sometimes it's the capillary size. Okay, suppose your smart capillary size is small, so they need to reach very quickly. Sometimes capillary size, so you will tune such hardware parameters so that you will get the small value of tau. So this way, when you want to build the measurement system, you have to build the hardware or tune the hardware in such a way that tau will remain small. And suppose you are not building, you are just choosing some measurement system for your particular application. In such cases, you have to see the manuals and you have to see that the tau values and the smaller tau values you have to just select. So this is the way you should go and you should take some engineering decision. Okay. Now tell me if you have any query. Lot of things we discussed. Anybody has any queries? So first order and zeroth order, both the types we discussed. Okay. So, okay, you may let me know that whether you understood everything properly. Okay, nobody is responding. Maybe everybody is sleeping. Let's move on. So now let's come to a second order instrument. This is also very important, and many instruments will interact in real life is of second order. So if we have a coefficient n is 2, that means n means the order of the uh, differential equation or the order of the denominator is power, that is 2. Then there will be two coefficients of a2 and a1, three coefficients a2, a1 and a0, and there will be one coefficient b0, whereas there is no 0. So only b0 exists, and all the coefficients are constant, they are not changing with time. Just 1 minute, wait. Okay, so if you see the second order transfer function, so there will be a2, there will be a1, a0, and if we apply the Laplace transform, we have b0 divided by a2 s square, a1 is plus a0, like that. So we have Laplace transform, and we have such numerator and we have such denominator. So here you see for a zero order system there was only one constant k, which is the static constant. Here we have three constants. So you divide this equation 2.9 by a2, both the numerator and denominator. So numerator you will get one constant, which is b0 by a0. Denominator you will get two constant, which is a1 by a2 and a0 by a2. Okay. Sorry, you will get two constant, a2 by a0 and a1 by a0 plus 1. You can write like so. In a second order system, you have the three constants. One is b0 by a0, another is a2 by a0, and another is a1 by a0. So b0 by a0 again we call the static sensitivity, which represents the gain in the steady state. A2 by A1 is called the A2 by A1 is called the 1 by omega n square, or omega n is called as the unmapped natural frequency, and zeta. So omega n is A0 by A2. A0 by A2. That means on the top there will be S square by omega n square, and zeta will be A1 by 2 root over A0 A2. So if we take the gains in such the constant in such a way, Hs will become k by s square by omega n square plus 2 zeta s by omega n plus 1, and we'll get k omega n square divided by s square plus 2 zeta omega n s plus omega n square. So this is the way we can write. And so you see, if you see the equation 2.10, so there are three constants. One is k, another is omega n, another is zeta. And these three constants have the three names. K is the static sensitivity, because if it is the steady state reaching, the gain, input output gain, is defined by the K. And now the omega n is called the undamped natural frequency of the system. That means if there is no damping, the frequency of oscillation will be omega n, and zeta will be damping ratio. That means how much the system is damped. So if we have a second order instrument, we can write the transfer function like that, and we need to know k, zeta, n, and omega. Now let's come to an example. What may be the example of a second order system? So before that, let me see if there is any query. There is no query. Okay. So what may be the example? So all of you have seen that galvanometer maybe in before coming to IIT in your science lab, or you have seen the in physics lab you have seen the galvanometer. So the galvanometer is a very good example of second order system. So how does the galvanometer work? Let's quickly describe. So there is a permanent magnet, as you see, and there is so it has two poles, north and south, and there is a moving coil. That means the coil will move, and there is an iron core. So the iron core is placed in between the magnet and the moving coil. That means very thin coil, insulated coil are owned. Coil is owned on the moving of the iron core, and there is a spring. You can see on the picture there is a spring with associated with there is a spring associated with that the the moving iron core. Actually, there is a rod along which the iron core can move, and with the rod there is a spring. Now, suppose there is some current passes through the moving coil, and when this current passes through the moving coil, this moving coil gets deflected because there is a magnetic field and current is passing. Moving coil, so the moving coil goes deflected. When it gets deflected, what happens? The spring gives the restoring force. Spring acts such a way that it opposes the deflection. So as a result, these two will sometimes, after sometimes, if you give a step input, these two will be in equilibrium, and then the pointer will be deflected at some angle, and it will remain on that. So in such a case, when the pointer is deflected and remain in that, you will get the steady state. But before reaching the steady state, it will not immediately reach the steady state. As it was deflected, it will be sometimes overshoot, and it will come down and oscillate small way, and then gradually it will get the steady state. So this instrument, if you model, because there is a damping associated with it, there is a spring restoring force associated with it, as the iron core is moving on the um, here, and there is the inertia, so damping is associated with it. So you have the damping, you have the restoring force or spring constant, and you have the deflecting force which is caused by your current passes. So the three forces are there, so this will be a very good example, will be a very good example of the second order system. So D. Arsenwall galvanometer, it is a very good example of second order system. So again I am reading. It consists of a rectangular coil wound around a soft iron core that is suspended in the field of permanent magnet. The signal being measured is applied to the coil, and it produces a radial magnetic field. The interaction between the magnetic field, that means permanent magnet, and the magnetic field created by the movement of the current, it's it's deflect. It creates a torque, and this torque deflects the coil, and the restoring force is created by the spring, and the damping force is created by the air damp, and so, and ultimately if you give some step input, it will be deflected, goes up and down oscillation, and then it will settle at some point. So this is a very good example of a second order system. So now if you see what may be the output of a second order system. Let's see. So how we will get the output of a second order system? How we will get? So you have a system like this, equation 2.10, and you know that this is the Q0 will be this expression into Qi. Now if you have a Qi which is step input, and then if you do the Laplace transform, you will get 1 by S, and then you multiply it with the step input, and then you do the Laplace inverse, you will get a time domain expression. And let me see if I have the expression, it is written in the book or not. So Now you can see the book. So let's see. From the book only I am teaching the same things from the book. Zero order instrument is here, same thing. First order instrument I got, same thing. Now step response of a first order instrument I got it. Then ramp response that I will call. I will come very next class all that is come. Very quickly I am trying to see first order instrument, then second order instrument. Yes, this is the second order instrument. You see, they are saying that the example they are giving second order instrument. Okay. Then step response. Yes, this is the figure actually. This is from the graph. So the same figure is plotted here. You see the so the second order instrument. If you see the second order instrument, there may be three conditions. One is zeta. Based on the zeta, there are the three conditions, and based on such, there are the different type of output response. So zeta may be zero. Actually, there are four conditions. Zeta may be zero, zeta may be one, zeta may be less than one, zeta may be greater than one. So the expression is 2.10 can be solved with the help of Laplace inverse by including step response and taking the Laplace inverse. You will see if zeta equals to 0, that means there is no damping, and then if you solve that, you will get a output response curve A. You see the curve A, which is completely oscillating, not oscillation is not dying down. So here for output curve A, if the zeta is 0. Now if zeta is less than 1, that means it called a, if zeta is less than 1, it's called a underdamped system. So in such a case, you will get the output of B or C. Okay, so what is the output B? Here output B. You see, output B is certainly overshoot, then undershoot, but less magnitude, then overshoot, less magnitude, undershoot, less magnitude, and gradually settle. You see the curve C, it slightly overshoot, then undershoot, and then gradually settles. Okay, so the output B is for zeta point 2, output C is for zeta point 7. So if you see if the zeta is more, the overdamp will be less. And if you see the zeta is less, the overdamp, that means shoot up, will be high. So, but whenever zeta is less than 1, it is called the underdamped system, and in such a system, you will see the oscillatory input, but the oscillatory output, but the oscillation will die down and gradually reaches to steady state. Now, when zeta is increased further, or maybe when zeta is 1, then you see the output is D. So, here is the output, okay, when zeta is 1. You see the output never overshoots to the steady state value. It always undershoots and keep on going and going, going and gradually it reaches to steady state value. Now, if zeta is greater than 1, which is called the overdamped system, then it will be strikingly below and then will be reaching at very after a long time. Okay, so this is called the overdamped system. So for overdamped system, output readings creeps up slowly and towards the correct reading, and it takes a lot of time to reach the correct reading. So we prefer whenever we want to measure, we prefer to operate the measurement system under 10 so that it oscillates and reaches the steady state quickly. And this is output response of the second order system. For step response, there are ramp response, there are sinusoidal response that will come later. So now tell me if you understood these slides. Okay, there is no query. So did you understand, or you want to write something, or if you understood, you can write that. Okay, I understood. If not, so let's move to the last slide, which is this one. So whenever you see there are different parameters that I was stating. So in parameters associated with second order response, so step response of the second order system, there are the parameters called the response time. So the response time may be the rise time and settling time, that may be the same as the rise time is the 90% value of the steady state when it rises is called the rise time. Settling time is the time when it reaches within the 2% or 5% band and never go away, never goes away. So that is the settling time. There are other parameters which is called the maximum overshoot. There are other parameters which is called the peak time and all. So maybe next class we'll discuss all those things. Mm. So, and also we want to discuss what will be the output when we give the ramp input or the sinusoidal input. And there are various other parameters like the rise time, settling time is written here. Apart from that, there is peak overshoot or percentage of peak overshoot. There is peak time, and there are few other parameters that undamped natural frequency and overdamped or damped natural frequency, that is also there. Okay, and those things we'll be discussing, and we will be finishing the uh, second order system. Now, if you see the things we are covering, it is greatly from the mostly from the Dublins, and now you see that we have covered around 150 pages. So you keep on reading the Dublins and try to see the solved examples. We'll discuss more, but it is around 150 pages we have discussed. We'll go further, and tell me if you have any query from today's class. So if you don't have query in today's class, so then we may end here. So tomorrow we have class from 11 to 12, right? So that will be continuing tomorrow's class 11 to 12. And maybe from next week onwards, we'll drop the Wednesday class. We'll go with Monday and Tuesday class. We'll take 2 hours Tuesday class, and that is sufficient. And but this week, let's go for the Tuesday class, and we'll continue discussion on the dynamic behavior of the system. And a small part we left, which is the error analysis, that also we'll keep on discussing. So for the time being, if you have any query, you can definitely ask. If you have any suggestion, you can definitely ask. And these slides I am trying to send, it's a very high memory size. It is taking time. Maybe today I will send this. I will send the link. I will upload it on Google Drive and send the link so that all of you can download and read it properly. And you keep on reading the Doebling. That is the most important. So I am saying that from where I am teaching. And everywhere in the world, people teaches from Doebling. This is a very standard book. So you keep on reading the Doebling, each and every line. If you face any problem or any difficulties, or you don't understand something, you just ask me. That is the way we proceed. So today we can end here. If you have no query, if you have query, you can write it or ask it. And you also please attend the class. That is very important, because ultimately uh, there will be Viva, and the main performance will be depending on the Viva, because all of you will copy from each other in the exam. But still, I will take the exam and see that how people are copying. And but to grade it, we need to distinguish between one from one to other. Otherwise, everybody I have to give A grade. That is not possible. The Viva helps in that way. So although it is very painful to take Viva for 70 students, still I will go for that. Otherwise, it is very difficult to grade. And grade will be like the earlier way you get grade, like 5% A and then AB, like that. Okay. So let's end here. Tomorrow we'll be meeting around 11, right? 11 to 12. That's the class. We'll be doing this class, and then we'll continue. Okay. So thank you for attending the class. Now we can end here. Thank you all of you.